Alrighty, so I'm going to switch over to my screen here. So over here, I have the classroom page under classwork. Here I've posted part 2. So it's a PDF document and it's going to cover all the code. And if you need to copy, you should be able to copy this. All right. The other thing I want to point out is if you go all the way to the bottom of the document, down here we have a link. So I know it's a pretty lengthy document, but at the bottom, view the code. And for now, that has only been updated with the code from the previous week. So the code that we did, and it is the same code as the one in the document. So if you are kind of catching up or you don't have the code from last week, you can also download it from here. So if you go here and then code and download zip, right? And you should have all the files. Okay, with that out of the way, I'm going to, oh, we have over here. All right, so I'm going to go back to my files over here. I'm going to hide this. So jumper over here, and I'm going to open it with my editor. So if you have Visual Studio Code, you can do it like that. Now, last week, I actually had to cut it just a little bit short. There was one more thing I wanted to cover that we did not cover. And that is kind of creating this game manager class. So we'll go into that in a bit. It's actually covered in last week's document. So if you guys read ahead, you might have seen how we implemented that. But just because it took a little bit to set up all the stuff from last week, I left that for this week. So we'll have to quickly add that. So Sahil, if you want to just create the file, we're going to call it jumper.py. And jumper is just the name of our game, if you guys remember. And what this class is going to do is it's going to handle all of the game related stuff. So when we're drawing something to the game, when the game needs to draw something to the screen, or when the game needs to update some piece of logic. And this way we're going to be able to keep it kind of separate from, if you remember last week, we created this kind of main program loop. We have this while loop, and we wait for kind of a quit event, and we tell all of our stuff in the game to draw and update, right? The reason we're going to create this separate class is because right now we only have a player, right? And you can see we're just creating the player at the top here and updating and drawing it here, right? But once we start adding more features, if we just implement everything inside of main.py, it will work, but it'll be very disorganized. It'll be hard to follow. And it really helps to break down the game into tinier components, right? So that's what we're going to do. We're going to break down we're going to separate kind of all the game related stuff from this main program loop. And then inside of this game manager, we'll be able to have all of the game's objects and maybe even other managers for objects. And that way we can really compartmentalize. Sorry, that's a difficult word to say. All of the parts of our game into kind of separate files or separate classes, right? So that's what we're going to do. So in Jumper here, sorry that I switched away. We're just going to create this class, and inside we're going to have an init method, which is going to run when we create it, an update, which is going to run every single frame, and then a draw, which will be responsible for telling all of the things in the game to draw. So it's also going to be called every single frame. And so this handles all the logic related stuff, and this is going to handle all of the drawing related stuff. Now, if you remember, back in main, we created our player over here. But now what we're going to want to do is we're going to want to actually move that over into our manager class. So in here, you can see Sahil imported kind of player, right, which we defined last week. And we're going to create it here in the kind of init method. And all we have to do, this is really simple, right? As every time we update the game, we need to update the player, and every single time we draw the game, we need to draw the player. And it's really simple because that's currently the only feature in a game. And you're going to see today we're going to add another feature, and you're going to see that we're going to carry over its methods also into this kind of class. And we're going to be calling all of the game-specific stuff inside of this jumper class. So all of this information is available in day 1. So if you don't see it in the day 2 PDF, it's because we covered it in the kind of part 1 PDF. All right. Are there any questions like from last week or what we just right now covered? And if not, I can kind of move on. Also, if you guys want me to kind of, okay, what is the init function? So the reason it's called underscore underscore init is because it's kind of a method that every single class can have. And what it does is basically when we create it, so for example, when we call player and we have these two parentheses, it's creating a new player kind of object, right? And when we create it, it's calling this init method. So once it gets created, we can call this code on creation. So basically what's going to happen is when the game starts or when the player is created, right, init gets called, right? And the same applies for the jumper, so init again, right? And then every single frame, we're going to be calling update, and that's going to be responsible for all the logic. And then draw is kind of like update, but instead of being responsible for all the logic, it's going to be responsible for telling Pygame to draw things to the screen. So does that make sense? And you can kind of see if you open up on the PDF, we have those comments above the function. So we say one gets called at the start of the game, the next gets called every single frame, right? Okay. Good to know. All right. So that's all there is to it. Now that we have this jumper implemented, we need to actually carry this over to our main file, right? So currently we're creating the player inside of here. What we actually want to do is have our game here. So we can kind of remove the player and we're not going to be using that anymore. And since kind of player and jumper kind of use the same structure, we can basically just swap out player for a game because they both have an update and a draw, and they're kind of accomplishing the same thing. At this current state, jumper is basically just passing on all of its responsibilities onto player because that's the only thing that's inside of it. But later it'll be passing over its responsibilities to other objects in the game. Like when we add platforms today, it's going to also tell platforms to update and draw. And that way we only have to call one update and one draw inside of our main file. Keeps things kind of simple. Awesome. So now that's out of the way. Next up, what we're going to want to do is actually fix an issue in our game. So I'm going to quickly run the game just to make sure that it's all working. And there you go. You can kind of see our player falling. And I know it might be just a little bit laggy, but imagine it kind of smoothly falling from the top downwards. And if you have this code on your computer, you can also run it and have a look at what it's like. Now there is, however, a problem. Sahil, would you like to kind of cover what that is?
Yeah. So on different computers, right, depending on how good the computer is and how fast it is, right, it will look different because right now we're updating the game every frame and we're changing the player's position and velocity every frame. So on some computers that may be faster than others. So because of that, right, it'll look different if we have the same values for each computer.
Right. So you can imagine on kind of a faster computer, this update will get called more frequently per second, right? Because it's able to process this much faster, which means it's able to loop over this more times per second, right? And when we do that, because if you kind of look, for example, in player, we're just applying this velocity onto it. What happens is because this gets called more frequently, on a computer that runs faster, everything moves faster. On a computer that runs slower, everything moves slower. And so what we want to fix is basically instead of moving all of these things relative to each frame, we want to move them relative to time, if that makes sense. So instead of moving them, say, 5 pixels per frame, we want to move them 5 pixels per second or per millisecond, right? Because time is going to remain constant across all computers, right? Each computer is going to understand 1 second as 1 second because they're wired up to do that. But as of right now, what's happening is the game's running faster on faster computers and slower on slower computers, and that's reflecting in kind of the state of the game as well. So the way we're going to kind of implement this is, and we covered this in the document, so I'm just going to show you guys over here at the very top. We're going to use delta time, right? So we kind of describe this issue over here about how we have kind of the game running faster on faster computers and slower on slower computers, right? And so what we're going to want to do is add this delta time. But what is delta time, right? Delta time is just the time between one frame and another frame. So if you imagine a computer running 60 frames per second, right? There's going to be a lot more frames within that second, obviously, right? So because of that, the spacing between each frame is going to be smaller. There's going to be less time in between every single frame. Whereas maybe a computer running at 30 frames per second, right? We're going to see these increments of time being larger, right? So we're going to use this change in time to figure out how to actually move objects in our game, and that way everything will move smoothly. So we even kind of have this mathematical explanation if that kind of makes more sense for you guys. I know the intuitive explanation might make more sense for some people and the math explanation might make more sense for other people, but basically what we have is right now the velocity is describing how many pixels we move per frame, right? And what happens is we use this velocity, right? And the amount of pixels we travel over a period of time is the number of frames that occur in that time times the velocity, right? So you can imagine that velocity, right, gets scaled by the number of frames that happen. And so the more frames there are in a period of time, the faster it moves, right? Because we add this velocity more times, right? But what if we add the time it takes for a frame to happen? Well, we know that the number of frames is, sorry, the number of frames is going to be like 60 or something, right? But the time it takes for one frame to happen, say we're using seconds, will be 1 over 60, right? Because we have to fit 60 of them in a second, right? So what's going to happen is when we multiply those two, 60 times 1 over 60, those will kind of cancel out to 1 because we're multiplying here. And what will happen is we'll get pixels over time is equals to velocity, which is kind of what we want. We want the velocity to affect how many pixels we're moving over a period of time, not by how many frames we're moving. So hopefully that makes sense. And so with the other explanation, what I'm saying is basically that if a computer is running faster, we're going to move the player at smaller increments, whereas if the computer is running slower, we're going to move the player at larger increments of time, right? So is there kind of any confusion about what this change in time is going to accomplish? And you'll see it in code as well. We'll kind of implement it in just a second. So I'm going to go back to the player, right? And over here, you guys can see we're kind of updating the position and the velocity every single frame, but we don't really care about how much time has passed. We're just doing this every single frame. So, Sahil, do you want to implement that real quick?
Yes.
So, in player.update, we're going to add a new value, and for now it's going to be undefined. I'm going to kind of explain what's going on here, right? This is going to be that change in time. So, for example, 1 over 60, right? And we're going to multiply the velocity by this every frame. So if you imagine we're in a perfect world, the frame rate is consistent. It's a consistent 60 frames per second. That means this is going to be, for example, 1 over 60 of a 1 over 60th over second, right? And if you add those all up, right, you get a whole second, right? And likewise, when you add up all those velocities that were multiplied by that, you're going to get the kind of the change in position per second, right? And in this case, actually, delta time is going to be milliseconds. We'll see why in just a bit, but we're going to use milliseconds for delta time. And then this logic carries over to the velocity and self-acceleration times delta time. So over here, we also multiply it. The reason being, we want the acceleration to represent how much the velocity changes by every second, not every frame. Because otherwise we'd get really weird results if one's shifting and by time and one's shifting by frame, right? So we want to have this affect both. And so now, when we pass in the appropriate delta time into update, everything should move uniformly across every type of frame rate, right? So 30 FPS, 60 FPS, right? FPS being frames per second. It'll run consistently because kind of the number of frames and the time it takes for frames cancel each other out. So that's why we're adding this multiplication. Now, you might notice we add a new parameter, so now we actually have to add that, right? And where we call player.update is in jumper.update, but there's really no way for us to know how much time has passed yet. So we're going to do that in our main file. And here we're just going to, again, take delta time as a parameter and then pass it in to self.player.update over here, right? And then I'm going to save these files real quick. In main, we're going to want to, again, pass in this delta time. Delta just meaning change in, and time being obviously time, so the change in time, right? And we're going to actually want to figure out what is this change in time. So the way we're going to find this change in time is by knowing when the previous frame happened and when this frame is happening, right? That way we can kind of find the difference in time. So to do that, we're going to have to be constantly keeping track of what the time of the previous frame is, and we're also going to have to get the time of kind of the current frame. So let's do that. We're going to start out by defining it at the top of the while loop, just as kind of a starting time, and we're going to use pygame.time.getTicks. So what pygame.time.getTicks does is it gets the number of milliseconds that have passed since the game has started, right? So you can imagine I click play, right? This is 0. Then a second passes, it's now 1,000, and another second passes 2,000, so on and so forth, right? And it's going to be an integer, right? We don't need too much precision, so it's okay if we don't have more precision than a single millisecond. This will do, right? And this will make sure that it runs uniformly across everything. The next thing we're going to need to know is the current time. So every single frame, right? Every time we enter this while loop, right? Because it's going to be looping continuously, we're going to have to get the current time, right? And then to find the previous time, or sorry, the delta time, yes, the delta time, we're going to have to get the previous time and get the difference between the current time and the previous time. So you can see current time is always going to be ahead of the previous time, right? That should make sense. And what this will do is we'll find the difference, so the change in time. And then lastly, once we find this change in time, we're going to save the current time into previous time so that when we enter this loop again, we'll have the time from the previous frame, right? And you can kind of imagine this repeating over and over again, right? So we'll have the game starts, we'll get the time when we enter this loop. So these will basically cancel out. It'll be 0, right? Delta time will be 0, right? Then we'll store that time into previous time, and then the next time we enter this loop, right? Note that this is outside, right? We'll get the current time, which will be a time that's roughly like a 60th of a second, for example, and then we'll find the difference between that time, and that will be that 1/60th of a second, and then we'll save that again, and it'll kind of repeat. Hopefully that makes sense. Basically, we're finding the amount of time it takes for all this code to run, because it's obviously not running instantly. It's running very quickly, but not instantly. Again, like, if there's any questions, feel free to ask with your mic. You can interrupt. I'm not going to be upset. You can also ask in the chat. I am keeping my eye out on chat, so hopefully there's that.
Can I see Jumper for one moment?
Yep. So that's just over here. It's really simple. And if you ever need to look back on anything, or if I kind of switched out of something, don't forget there's always kind of the code in the PDF document. So I totally don't mind switching over, but just in case you need to look back on some code, that's also available in the PDF, right? So all the code we're writing today is in that PDF.
This is going to be on the Google Classroom right after, right?
Yeah, it's already on the Google Classroom, and we'll post the actual like final code also onto that GitHub link I showed. But all the code's already like written in the PDF document, and that's under classwork. Okay. So next up, we've implemented delta time. And so what's going to happen now is everything's going to run relative to the amount of time that has passed, right? So we've only have the players so far, so that's good, right? And I'm going to run it, and you're going to see it's moving even slower now, right? And that's because before my computer was running so fast that things are moving faster than they should be, right? And on your computer, things might have been moving super slow, right? If you use the same values as me. So what I'm going to do now real quick is, Sahil, do you want to do this? We're basically going to adjust these values over here to be like what the final game uses. So for example, the gravity and I believe the velocity might be a little different. No worries if it's not. So I'm just going to set this value to 0.0015. That's kind of the gravity we use in the final version. And for now, for testing, we'll set the velocity to 0.5. That should do. Okay. So next up, now that we've implemented this, what we're going to do, and again, you can see this code is all over here in this document that we've written out. We'll be adding platforms. So
Quickly, before
yep.
you talk about platforms, you might want to show them using time wait to make it look a bit laggier and show them like what it
Oh,
actually
that's
looks
true.
like.
That's true. That's true. So I can do that. Basically now, you can see when I run this game, it's going to fall relatively quickly. I'm imagining you guys, how laggy is it, Sahil? Can you guys see that it's falling?
It's quite laggy, yeah.
Okay, so what I'm going to do is I'm actually going to multiply delta time by like 0.25 just so that it runs in slow-mo so that you guys can actually see what's happening. So is that better now?
Yeah.
Okay, and what I'm going to show is that if the game were to run slower, and you guys don't have to copy this over, I'm just showing, if the game were for some reason lagging, and I'm just going to fake this lag by making the program wait every frame, right? You're going to notice it's going to be choppy, and maybe this will be more visible kind of in the final video, but even though the game is lagging, the player's still going to move at the same speed. So I don't know if it's really visible that it's more laggy now because the stream itself was already laggy, but if you actually go back and watch the video recording, which I'll post afterwards, you'll definitely see that kind of the players moving in jumps, right? But at the same speed. So hopefully that makes sense. Okay. So next up, we're going to be adding platforms. Sahil, do you want to kind of cover what we're going to do? I can start working on the files.
Sure.
Just kind of the beginning, not the collision detection. So
Okay, yeah. So we're going to be making platform objects just like we did with our player, right? So same way we're going to be making a class called platform.py, and we're going to be making a class in there called platform, right? And then we're going to set up some base values just like in player, where we have our width and our height and the color, right? But unlike player, platforms don't need to be updated every second. Nothing's happening to them. So all we need is an init class or an init function and a draw function.
and in here, I believe we need X and Y. And the reason we're going to want this is because we're going to have multiple platforms in the game, and we want the game itself to be able to decide where the platform spawns. We're going to pass those values into platform rather than having the platform itself figure out where it's going to be positioned. Right. And so in here, we're going to have a few kind of predefined values as Sahil mentioned, right? And I'm going to just quickly look at my cheat sheet here. So we're going to have a width and a height, and we're going to set this to 200 wide. So that's going to be roughly a third of the screen in terms of width, and then 5 pixels in height. So it's going to be very skinny but wide, right? Hopefully that makes sense. And then we're going to also have a color kind of like player because we need that for drawing, right? So that's going to be 0, 0, 0. And that's going to be a black color. Next, we're going to need a position, right? And we're going to use a vector for this again. So this is basically the same idea as player. You're going to notice a lot of similarity between, and this is not 0, 0, this is XY, sorry. Right? And to draw it, we're going to need to know that shape again, and then we're going to need to tell Pygame to draw that shape, right? So I'm going to do r equals Pygame dot rect, and then we're going to need the left, the top, the width, and the height. So the left and the top is our top left position, which we have. That's position, so position.x, position.y, and then we have our width and the height. So self.position.x, self.position .y, self.width, and self.height. And I misspelled that, but that's fine. Okay. And once we have the shape defined, we're just going to have to tell the game to draw it. And we're going to pass in color and then the shape. So that's R. Awesome. That's all there is to our platforms, really, just drawing them. And then we'll be figuring out kind of collision detection with them in just a second. But just to show that these are working, I want to quickly implement it in our jumper. So we're going to kind of create a test platform. And to do that, we're going to have to import it. So from platform, import platform. And then inside of here, you don't have to actually copy this down. This is just to make sure that it's working, right? We're going to do, we're going to create a new platform. And we're going to put it at 0, 0 for now. And I'll show you guys how to, sorry, I don't know why I wrote that way. So self.test platform should equal this. And we're going to put it at 0, 0 for now.
The tabs got messed up, I think.
I think so. It's fine. I'll fix it. So spaces, boom, there. All right. And then every single update, we're going to have to tell our platform. Actually, no, never mind. I forgot. Our platform does not have an update again. So if you look here, we didn't define update. So we don't have to call anything in here. We just need to tell it to draw. Yes, if you want to put that there. And so if you save, when I run this, so I'm going to just save it. When I run this, you're going to see this kind of little bar over here, and that's our platform. So are you guys able to see that? Hopefully. Right over there. Just at the top of the window. Right over here. Now let's try positioning it in the center of the screen. So we're going to do that just over here, not here in platform, in jumper. And instead of using 0, 0, we're going to position the center. Now remember that this is the top left kind of corner of the platform. So we're going to do screen width and screen height. But what this will do is I'm just going to quickly draw you guys a diagram. Right over here, if you imagine this as the center of the screen, right? If we create it at the top left, what's going to happen is it's going to kind of create the platform like this, and it's not going to be in the center of our screen. So to center it, we're also going to have to subtract half of the platform width and then half of the platform height, and then it'll be kind of positioned in the center. So we're going to do that right here. We're going to subtract platform dot width divided by 2, and then minus platform dot height divided by 2. There we go. And if I run this, now you're going to notice, oh no, what did I do wrong? Can someone spot it?
Did you forget to do screen dot width and screen dot height divided by 2?
These should be divided by 2. Good catch. Because we want it in the center, right? That would have been in kind of the bottom right corner. So good catch. There we go. So now it's in the center. And the last thing you might notice is our player's not actually interacting with this platform, right? We're only drawing it to the screen. So of course it makes sense. And in the final game, we're of course going to want it so that when the player falls into the platform, they detect a collision and then jump away from it. So that's going to be what we implement next. So let's go over to player, right? In here, what we're going to do is we're going to create a separate method that's going to be responsible for handling the collisions with all platforms in the game. So to store all platforms in the game, we're just going to use a list. And inside of here, we'll make sure we're not colliding with any platforms. And if we are colliding with platforms, we will resolve that and make the player jump, right? So when they're colliding, they'll jump up. Awesome. So we're going to call it resolve underscore platform underscore collisions. Awesome. So now what we're going to do is the first thing we're going to do to detect collisions is we're going to check if there is horizontal overlap with the player. And I've kind of prepared some diagrams for you guys so that you guys can kind of see what's going on. So if I just show you guys, hopefully this works. You guys should be able to see this. Basically, what we're going to do is we're going to take, for example, the right side of the platform, and then we're going to check if the left side of the player is to the left of the right side of the platform, right? And if it's not, then we know for certain it is impossible for the player to be colliding, because no matter where we move the player kind of horizontally, right, as long as they're to the left of the platform, right, like this player left, sorry, it's to the right of platform, right, it's not possible for it to be colliding. So that's going to be one case where we know it's not colliding. The other case we can check is the opposite case, right? So the player is to the left of the platform, right? The player right side is to the left of the platform's left side. So no matter where we move the player, it's not possible for it to be colliding, right? So those are going to be the first two checks we perform. And here, for example, you can see there is overlap, right? And that's because the player left is to the left of platform right. And if I were to actually move this around, you can see that under some configurations, it is possible for the player to be colliding with the platform. So in this case, we're going to have to perform other checks to make sure the player isn't colliding. But this will be our first check, right? And so to do this, we're going to need to know the player left, the player right, and then the platform left and the platform right. And there's going to be multiple platforms, so we're going to have to loop over all of our platforms. So let's implement that. So right here, Sahil is finding the left side of the player and then the right side of the player. So if you remember, the position is kind of the top left corner, and then the right side, we're going to add the player's width to get the right side. Then next, we're going to loop over all the platforms that will eventually be passed into this function. And for each of those platforms, we're going to find their left side and right side. And using these two, we can kind of look for this horizontal overlap. And if there is overlap horizontally, then we know that there's possibly a collision. So if the player left is less than the platform right, that means that they are overlapping. The left is to the, so the player's left is to the left of platform right. So that is, if I just show my slideshow again, that is this case. So you can see the player left is to the left of platform right. But also, the player right needs to be to the right. So if you imagine the player right would be kind of over here, and the platform left would be like over here, you'll notice it's also to the right. So that's going to go over here, this if statement. So at this point, inside of here, we know that there is possibly a collision. Now, once you know that there's possibly a collision horizontally, we need to check if they're actually touching the platform. So Sahil, you can wait on that just a second. if you guys look at this diagram over here, you can see that in this case, right, there was no collision because there's kind of this distance between the top of the platform and the bottom of the player, right? And when those two are touching, that's when we want to kind of resolve a collision. So when the two are roughly equal to each other, that's when we want to resolve a collision. Now the naive way to implement this would be to check if the player's bottom is the same as the platform's top, right? So you can imagine kind of if player or self dot position, so that's the player's position, dot y plus self dot height equals the platform dot position dot y. And in a perfect world, this would work, right? However, because of the way we are simulating our game, in most cases, this would basically never happen, right? And let me actually show you kind of this diagram which shows. So remember that although to us it may appear that the player is kind of moving continuously across the screen, in reality, we're kind of moving the player in steps. So each frame, they're going to move by a certain position. And these frames are happening in such quick succession that to us it appears the player is moving continuously. But again, that's not actually what's happening on the computer, right? And so what's going to happen is you're going to notice as these frames increase, the player's kind of bottom is going to keep going down, but it goes down in steps. And what happens when we go right past platformer Y? In none of these two frames did the bottom of the player equal the top of the platform, right? And so because of that, what will happen is the collision doesn't get detected and the player will fall through and they'll be confused. So how do we solve this? If we're not detecting collisions because the player is jumping around, because we're simulating these discrete steps, right? The movement is not continuous. How do we do this? How do we detect it? The solution is to account for some error, right? And we'll introduce this in our code in just a second. This symbol right here means epsilon, right? And it's just kind of the letter used to denote an acceptable amount of error. In this diagram, it is like extremely exaggerated, right? Remember that in our game, the frames are going to be much more closer together, right? But in this diagram, I've just exaggerated so that it's very clear, right? This epsilon is going to account for some room of error between the platform Y and the bottom of the player, right? And so what will happen now is this is the exact same simulation, right? Frame 1, we're above the epsilon. Frame 2, we're above the epsilon. But then in frame 3, we're going to see, well, you know, the top of the platform and the bottom of the player, they're close enough. So we're going to resolve the collision, right? So even though we're actually not quite touching, in our game, this is going to be very close. It could be less than a pixel. When we enter this area, we're going to resolve it. And so in a way, we're going to prematurely resolve the collision, but because we're moving in the steps, it's going to look perfectly fine in our final game. And this epsilon will help solve the kind of error where we skip over the exact Y position where the collision would occur, right? So now the last question is going to be, what is this epsilon, right? What will it be? And the way we're going to determine that is based on how fast the player is falling or how big these steps are. So in our case, this epsilon is going to be kind of the rate of change at which the player is falling. So you'll notice these steps, right? The amount of distance we cover in these steps vertically, that's going to be what our epsilon is, right? And this way, the player will be guaranteed to kind of enter this difference and the collision will get resolved. Hopefully that makes sense. I'm going to real quick open up my Meet chat, make sure I'm not missing something. And if there's any questions about this, I would love to clear it up. So right over here, we kind of had our naive implementation, right? What we were checking is if the bottom of the player, right, this part, is equal to the top of the platforms. What we're going to do right now is we're going to actually rearrange this, right, to instead be the difference between the two. So if kind of the self.position.y plus the self.height, so that is the bottom of the player, minus this is equal to 0. And this is the exact same thing we had before. This is that naive case. We're basically now just checking if the difference between the two is 0, aka they're touching, aka they're the same, right? But we've rearranged this. And what this is now is kind of the space in between the platform and the player, right? So if we look back at the diagram, that's going to be kind of the space we have, right? And what we're going to do is we're going to check if this space between the player and our platform is smaller than this epsilon, the acceptable amount of error, right? And if it is, then we know they're practically colliding and we can resolve the collision, right? So what we're going to do is, instead of having equals equals 0, we're going to check that it is less than epsilon. And over here, Sahil real quick typed it out. I'm going to give you guys a bit to copy this. Epsilon. And I'm going to have to explain what this is. So this epsilon is finding how much our player is going to move by, right? And that's going to be our kind of vertical velocity times delta time, right? Because that's how much we're going to move. That's how much we're going to step the player's position in a single frame. So this is basically calculating the same thing over here for self.position. And it's finding the step at which we're going to move vertically. And we're going to use this as the room for error, right? Because this is kind of the furthest it could be away from the platform before it kind of skips ahead of it, right? Hopefully that makes sense. And I'm just going to take the absolute value because it is technically possible that the velocity is negative. And in certain applications, you might want to be resolving the collision when the player is going upwards or whatever. Basically, my point is going to be that epsilon should always be a positive number. And because velocity.y can be a negative number, we're going to get its absolute value, which is basically just making sure the value is positive. All right, and we're multiplying by delta time because that's kind of the time step. And then over here, again, we're going to use the absolute value. And the reason we're going to do that is because in our example over here, right, the player was above, right? So you could say that the difference was positive. But if the player was actually below it, so like this, then the difference would be negative. And in fact, this epsilon applies also in the negative. So it's kind of both, right? But keep in mind that this is 2 epsilon, right? The total distance, right? So the distance in one direction is epsilon, which is what we're going to be comparing with, because that we're finding the difference between the two y positions, right? And so that's what we're accomplishing over here. We're basically accounting for some error in our simulation because we're moving the player in these steps so that we guarantee that the collision is detected, right? So that the player can't just skip through the platform because it's moving in these increments, right? And so at this point, right, over here, we know that we have a collision, right? All that's left now is to actually kind of resolve this collision, right? Figure out what we're going to do. So in our game, what we're going to want to have happen is when there is a collision, we're going to want to have the player jump, right? But if you think about it, there's also one more case that we want to consider, and that is that the player is falling. If you remember in the original game, the player kind of jumps through the platforms, and they only jump off a platform once they land onto it, right? So if I am just to fly through a platform upwards, nothing will happen, but when I land on it, I jump again, right? That's just kind of the mechanics of our game. And so the way we check if the player is falling is just basically by checking if our y velocity is greater than 0. Because if our y velocity is greater than 0, that just means our player is moving in the positive y direction And the positive y direction in this case is downwards, right? Because top left is 0, 0, and then the bottom right is our screen width, our screen height, and those are positive values, right? So this is checking over here if we're falling, and if we're falling, then we want our player to jump. Now, we wrote self.jump over here, but you might actually notice that we don't have jump implemented, right? And so Sahil, do you want to just quickly explain what this jump is going to do?
Yes. So we're going to be making a jump method, and we're just going to be increasing, or well, decreasing the velocity of the y, right? The y
Well, we're
value
not
of the
going to be
velocity.
decreasing it. We're going to be setting it to a value.
Sorry, yes. Right, and that way, over time, the character will move up.
Right. So
if we just set the position up, it would just look like it's teleporting, right? And we don't want that. We want that to jump and go up over time. So that's why I'm doing velocity instead of position.
Right. And then over time, our gravity acceleration will kind of pull down on this velocity, and so we'll get kind of a upwards leap, and then they'll start falling again, right? And so we're going to set this value to negative 0.8, but because we don't like random numbers in our code, we're actually going to define a new value. I'm going to call it jump power. You can call it whatever you want, but this is basically going to be the rate at which we send the player upwards, right? When they jump. I'm going to call it jump power, and we're going to set it to negative jump power, self.jump power, right? Because we want to move upwards, and upwards is negative. Awesome. That's literally all you need for jumping, right? It makes sense. We're telling the player to move upwards, and so that's what is going to happen. When we jump, it's going to move upwards, right? So now, what's happening in our resolve platform collisions is we're getting the left side and the right side of the player, we're getting the left side and the right side of each platform, and we initially test for overlap horizontally. If there is horizontal overlap, we know that a collision is possible, and then all we need to check is that because we know there's horizontal overlap, we only need to know for that, we need to know if we have that vertical overlap, or if the bottom of the player is touching the top of the platform. And because we're moving in increments and not continuously, we have to account for a little bit of error. So that's what this epsilon is accomplishing. And once we do all of that, we know that the player is colliding for sure. All we have to do is resolve it. So if the player is falling, we jump. And that's all there is to this resolve platforms collisions method. It's a lot to explain, but I hope that it makes sense. And I'm going to check again. Are there any questions in the chat? No. Okay, so I'm assuming we're good. If there's questions, please let me know. I can pause at any moment. Okay. And Sahil, if you want to just keep an eye out from time to time, that would also be helpful. Okay.
Yep.
So next, we have our platforms. Now we need to, we have our platform, we have our player which can resolve these collisions. Now we actually need to tell the player to resolve collisions. And the way we're going to do that is we're going to pass in that list of platforms, right? So in here, we're going to call self.player.resolve platform collisions. We have delta time, but we don't have a list of platforms. So what we're going to do is instead we're going to convert this over here into a list of platforms. So just like that. And for now, this is just temporary. Our platforms list will only contain one platform, and that's going to be that platform in the center of the screen. In the future, the reason we're making this a list is because we're going to have multiple platforms. We're going to be constantly adding new platforms, deleting old platforms as the game kind of moves upwards, right? And so that's why we're using this list, because there's going to be multiple platforms in the future, and we want our player to check collisions with all of the platforms, not just one of them, right? And now we can pass in this self.platforms list. And the last thing we need to fix in here is we're currently doing self.testPlatform.draw. So Sahil, if you want to do that. Basically now we just need to loop over each platform in this platforms list and tell each single platform to draw. That should be pretty straightforward, right? And awesome, you can see we've added a bit more functionality to our game, and now our jumper class is growing a little bit more, right? And you can imagine if we were implementing in this main file, then this would already make main more complicated. And as we keep adding and adding and adding more features, it would become too cluttered. So I'm really happy that we got this game manager class implemented. And awesome. I think that's all we need to see collisions actually happen in our game. So if I run main, and I'm going to slow this down again just so that you guys can actually see what's going on. So on your screens, this should run much faster. I'm just slowing down time by multiplying delta time. And you'll see the player kind of falls, collides, and it's beautiful, right? And even though we have that tiny, tiny, tiny bit of epsilon we're accounting for, nothing looked off. It looked like our player actually touched it. And that's probably because that epsilon, when running at a high enough frame rate, is probably tinier than a pixel. But because we have kind of sub-pixel values, right, like 0.5 of a pixel or 0.25 of a pixel, right, chances are that those two positions would never have equaled each other. And if we were just to perform that naive check, then the player would just kind of fall through because of our faulty logic. Awesome. So that right there is collision detection. And I think there's just one last feature before we wrap this up that I wanted to implement. And that is basically in the final game, what's going to happen is when the player goes off the right side of the screen, they'll get teleported to the left side. And then when you go off the left side, they'll get teleported to the right side. So Sahil, do you want to kind of explain that as I implement it?
Sure. Just give me one
Right,
second.
so right above update, again, in player, we're going to implement a new method. And it's going to be called screen wrap.
So for screen wrapping, right, what we basically want to do is as a player goes off the left or the right side of the screen, we want to move them to the other side, right? So what we could do is we could simply teleport the player to the other side, but that's not going to look natural, right? So what we want to do is teleport them a bit before the side where they're going to be, right? This way it looks like they're coming out of that side of the screen instead of just randomly moving there, right? So the way we could do this is we could check if the X position, right, is greater than the width of the screen. And this would mean that they're past the right side of the screen. And if they are, right, then what we're going to do is we're going to make their position their negative width. So this would be just a bit before the screen. And this way it looks like they're coming out of the screen instead of just teleporting.
And then for the other case?
So for the other case, it's similar, right? We're going to be checking if it is their negative width, and this would mean that they're just a bit on the side of the screen. And if so, we're moving them to the screen width, so on the edge of the screen. Right.
Mm-hmm. So just to kind of reiterate over what we're covering, so remember, position is kind of the top left corner position. So if we move over to the right side and past the right side of our window, right, then the position is going to be greater than the screen width. And then the reason we're teleporting over the player by setting their position to negative self.width is because you can imagine if we set the X position to 0, then what we would get is the player would teleport their left side over to the edge of the screen, and you would see the player pop into existence. So instead, we want to teleport the player along the right side. And the right side is going to be another self.width pixels away. So what we're doing is basically 0 minus self.width, and this means that the right side of the player is aligned with the left edge of the screen, and 0 minus self.width simplifies to negative self.width. And then the same thing goes, right? We're checking basically if the right side of the player goes off the left side of the screen, and if so, we're teleporting the left side of the screen along the right side of the screen. I know, that is definitely a mouthful, but hopefully that kind of makes sense what's going on. If anyone's confused, I can try draw a diagram, and maybe that will make it more obvious what's happening. So let me know in the chat if anyone's confused. And lastly, we've created this, but we're actually never calling it anywhere. So in update, we just need to tell the player to perform this check, right? And so we're just going to, in update, call self.screenWrap, right? And this will make it so that every single update, every single frame, they're going to check if this is true, if they go off the screen, and it's going to perform all the teleporting and all that stuff for us. And so what this will do now is if I actually run the game, the player is going to fall down, hit the platform, and then when they go off the edge of the screen, they're going to come out from the other edge of the screen. So I can run this in even slower speed, just so that you guys can see it, right? Is it running? There we go. So you can see the player falls, they hit the platform, they bounce, and then pay attention to when it goes off the edge of the screen. The second they hit it off, they're going to teleport kind of off screen and right back onto screen, right? So that's pretty cool. We've gotten a lot implemented today, and I know some of it might have been confusing. So if there are any questions, then stick around for sure. That's all for today. Remember, I'm going to be posting a video recording of today's lesson, as well as the PDF is already posted, and that contains all of the code we've implemented today. For the jumper class, you can look at day 1 or part 1. And lastly, I'll upload today's code on the GitHub page, which is linked at the bottom of the PDF. And that's all for today, guys. Thanks so much for coming. I hope you guys learned something new and that you guys enjoyed this. So yeah, if you're, yeah, everyone have a nice day, and see you guys next week.